Is space itself an illusion? Join us as we explore one of physics' most radical ideas, that space and time emerge from quantum entanglement. Space may not be fundamental. Instead, it emerges from quantum connections forming an information network beneath reality. First, let's understand how we traditionally think about space and time. In Einstein's general relativity, space-time is like a smooth fabric that curves around massive objects. This is how we picture space-time, a continuous grid that gets warped by massive objects like planets and stars. The metric tensor g mu nu describes distances in curved spacetime. This equation is the foundation of general relativity. In this classical view, spacetime is continuous, smooth, and fundamental to reality it's. But quantum mechanics reveals a problem with this smooth picture. Here's a key question. What happens when we zoom into space at the smallest possible scales? At the Planck length, about 10 to the minus 35 meters, quantum effects dominate and space-time breaks down. At this scale, space becomes quantum foam, a chaotic, fluctuating mess where smooth geometry no longer makes sense. This creates a fundamental conflict. General relativity needs smooth space, but quantum mechanics says space can't be smooth at tiny scales. The solution may lie in quantum entanglement, one of nature's strangest phenomena. When particles are entangled, they share quantum information instantly, no matter how far apart they are. This equation shows an entangled state. The particles are correlated in a way that can't be separated. Crucially, entanglement connects particles in a way that seems to bypass space-its. This raises a profound question. What if entanglement is more fundamental than space, not the other way around? A breakthrough idea connects quantum entanglement to the geometry of spacetime. The ER equals EPR conjecture says entangled black holes are connected by a wormhole, a bridge through spacetime. Einstein-Rosen wormholes equal Einstein-Podolsky-Rosen entanglement. Geometry equals quantum correlation. This suggests that wormholes and quantum entanglement are actually the same thing viewed from different perspectives. Now we arrive at the core idea. Space itself emerges from quantum entanglement. Imagine a network of quantum bits connected by entanglement. The pattern of these connections creates the illusion of space. Regions with more entanglement connections appear closer together in the emergent space. The Bekenstein-Hawking formula connects entropy S to area A. Entanglement entropy builds geometry. In this view, distance isn't fundamental. It's determined by how strongly quantum systems are entangled. A precise mathematical relationship connects entanglement to geometry. The Ryu-Takayanagi formula, entanglement entropy of region A equals the area of a minimal surface divided by 4 times Newton's constant. To find how entangled a region is, you find the smallest surface that bounds it in a higher dimensional space. This formula is revolutionary. It proves mathematically that geometric quantities emerge from quantum information. The holographic principle takes this idea even further. Information in a volume is bounded by the area of its boundary, like a hologram encoding 3D information on a 2D surface. A three-dimensional universe might be encoded on a two-dimensional boundary, like a hologram. This means the three-dimensional space we experience might actually be a hologram, projected from information on a distant boundary. Let's calculate how much entanglement creates space using real numbers. Imagine a spherical region of space with radius 1 meter. The surface area is 4 pi r squared, which equals about 12.6 square meters. Using the formula, entanglement entropy equals area divided by 4 times g times h bar. This gives approximately 4.5 times 10 to the 42 bits of quantum information. That's how many quantum correlations are needed to create just 1 cubic meter of emergent space. What are the implications if space truly emerges from entanglement? The hierarchy of reality is inverted. Quantum information is most fundamental, entanglement emerges from it, and space-time emerges from entanglement. Quantum information becomes the deepest layer of reality, more fundamental than space is. Space becomes an emergent phenomenon, similar to how temperature emerges from atomic motion. Here's an analogy to understand emergent spacetime. Think of the internet. Web pages seem to have locations, but they're really just connection patterns in a network. A web page doesn't have a location in physical space. Its apparent location comes from how it's connected in the network. Similarly, points in space may not have fundamental locations. Their positions emerge from quantum connection patterns. Is there any experimental evidence for emergent spacetime? Here's the challenge. How can we test whether space is truly emergent? Black hole information paradox provides hints. Information entering a black hole must be preserved through entanglement. Black hole entropy scales with surface area, not volume, suggesting information lives on boundaries. Black hole entropy equals Boltzmann's constant times area divided by 4 times the Planck length squared. Future gravitational wave observations might reveal quantum structure of spacetime at extreme energies. The most concrete realization of emergent space comes from string theory. A gravitational theory in d+1 dimensions is exactly equivalent to a quantum field theory in d dimensions without gravity. A 3-dimensional universe with gravity is mathematically identical to a 2-dimensional quantum theory without gravity. This correspondence proves mathematically that an entire dimension of space can emerge from quantum entanglement. Recent discoveries link emergent space to quantum computing concepts. Quantum error correction encodes logical qubits into physical qubits. The bulk space emerges from this redundant encoding. Spacetime geometry itself may be a quantum error-correcting code that protects information. Bulk quantum states are error-corrected versions of boundary states. Space emerges from redundancy. Emergent spacetime may finally unify quantum mechanics and gravity. A key question: why has it been so hard to create a quantum theory of gravity? Quantum mechanics and general relativity seem incompatible. Maybe we've been approaching the problem wrong. The answer: because we assumed spacetime was fundamental and tried to quantize it directly. But if space emerges from quantum entanglement, then quantum gravity is just the physics of entanglement. Scientists use tensor networks to model emergent space concretely. Tensor networks are quantum circuit diagrams, where nodes represent quantum states and edges represent entanglement. Each node is a quantum state. The connections between nodes represent entanglement strength. The geometry of this network becomes the emergent spacetime that we experience. Not just space, but time itself may be emergent. The second law of thermodynamics says entropy increases. This arrow defines time's direction. Time's flow may be the increase in quantum entanglement. As systems become more entangled, we perceive time passing. Time emerges as the growth of quantum correlations throughout the universe. Without changing entanglement patterns, there would be no flow of time at all. Emergent spacetime has profound implications for cosmology. The Big Bang might not be an explosion in space, but the emergence of space itself from quantum entanglement. The Big Bang is the moment when entanglement patterns began creating the emergent space we inhabit. At time zero, entanglement entropy was zero. Space and time emerged together as entanglement grew. Dark energy, causing cosmic acceleration, might be tension in the entanglement network as it expands. This hypothesis transforms our philosophical understanding of reality. Space is an illusion, a useful approximation that emerges from quantum information at large scales. Ultimate reality is not matter distributed in space, but quantum information and entanglement patterns. We essentially live inside a vast quantum computation, where space is an output, not an input. Where is research on emergent spacetime heading? Scientists are building quantum computers to simulate emergent spacetime and test these ideas experimentally. Quantum processors create entanglement networks that might exhibit emergent space-like properties. Researchers are testing holographic dualities using cold atoms and quantum circuits in laboratory settings. Teams are analyzing gravitational wave data for signatures of quantum space-time structure. Despite progress, major challenges remain. A key question: exactly how does smooth classical space emerge from discrete quantum entanglement? How many quantum bits would be needed to create a universe like ours? Estimates suggest about 10 to the 122 qubits would be needed based on the observable universe's horizon area. Can we derive Einstein's field equations directly from entanglement dynamics? This is partially solved, but not complete. Let's summarize this revolutionary picture of reality. The hierarchy of reality, quantum information at the foundation, entanglement emerges from it, geometry from entanglement, and space-time from geometry. Space and time are not fundamental aspects of reality, but emergent phenomena. Quantum entanglement weaves the fabric we perceive as space. Quantum information is the deepest layer of physical reality we've discovered. This emergent picture may finally resolve the century-old problem of unifying quantum mechanics and gravity. Let's conclude with the profound implications of this hypothesis. Space is an illusion, a useful approximation that emerges from quantum information at large scales. We essentially live inside a vast quantum computation, where space is an output, not an input,